In May 2010, I testified in front of the House Select Committee on Energy Independence and Global Warming, a committee that no longer exists. One of the witnesses at that hearing was Professor Will Happer, an eminent physicist at Princeton University, not a climate scientist. And Professor Happer made this statement in his oral and in his written testimony. Over the past 10 years, there has been no statistically, I think he meant to say significant, global warming. This is not at all what was predicted by the IPCC computer models. So the same models I've shown you all this afternoon. Now, Professor Happer did not provide any supporting documentation for this assertion here. So I felt that I really needed to do the science necessary to determine whether he was right or not. And this is from a paper that was published a couple of months ago in the Journal of Geophysical Research. And what we essentially did is looked at whether the class of computer models I've been showing you up to now, when run with human-caused changes in greenhouse gases, could they produce hiatus periods, 10-year periods with little or no warming? Remember this? So these are the satellite-based estimates of temperature change of the lower 5 kilometers of the atmosphere. Okay, so they show this overall warming trend of roughly 1 degree Fahrenheit. And Professor Happer was windowing in on this period here. Now this big spike here, so he was windowing in on the last 10 years of record essentially. This big spike is the 1997-1998 El Nino event. On average, El Ninos warmed the surface and the lower atmosphere when you average globally, and this was one of the biggest of the 20th century. So this is Professor Happer's starting point for his assertion. And near the end of the record, we have a couple of La Niñas. La Niñas on average cool the planet. So Professor Happer is essentially windowing in on one short, noisy period of record. Is that permissible? So first of all, can current climate models simulate such hiatus periods? That's the question we're going to look at here. And I really feel embarrassed to kind of show this at SCI here. This is my very crude, primitive attempt to make my own visualization of this issue here. It's a signal to noise issue. 10-year trends are noisy. So what we're going to do here is we're going to look at this satellite estimate of changes in the temperature of the lower atmosphere, and we're just going to march through 10 years at a time with overlap by all but 1 year and look at these noisy 10-year trends. And not surprisingly, you see that endpoint effects matter. Whether you end near a big El Nino or La Nina matters. 10-year records are noisy and strongly influenced by the year-to-year variability of atmospheric temperature. So, if you average all of those brown lines, not surprisingly, you beat down the noise a little bit, and the average 10-year trend is positive. So this shows you again that you can't cherry pick and just select one 10-year period of record there. So in order to address Professor Happer's claim, we used a satellite simulator to simulate these atmospheric temperatures in the same way that a satellite sees the temperature of Earth's atmosphere. And we looked at these roughly 24 models and many realizations of 20th century climate change. This is what they look like. So here are simulations of lower atmospheric temperature change in all of these different models. The y-axis range is identical in each one of these things. And you can do exactly what we just did in the observations. You can fit overlapping 10-year trends to these things and build up a sampling distribution of trends. And these are all simulations, again, with human-caused changes in greenhouse gases in them. Okay, so these are not undisturbed Earth simulations. They're all with human effects. And when you do that, you get this sampling distribution of 10-year trends in lower tropospheric temperature. And the key thing to note here is you have this big negative tail. So even in these simulations, you can, by pure chance, get 10-year periods when there's little warming or even when there's cooling. Now, if you plot the average of all the observed trends, which I showed you before, the average of all those brown lines there, the average observed trend is actually very close to the average of the model sampling distribution of 10-year trends. So Professor Happer was wrong, demonstrably so. Climate models can, even when run with human-caused changes in greenhouse gases, just by chance, produce 10-year hiatus periods. You can't engage in science by eminence of position, particularly not when you're testifying in front of Congress. That was my lesson from this. And I think it also illustrates that it is necessary to do the science in order to address the assertion it's all the sun, or global warming has stopped, or this is all a natural phenomenon. In each case, we need to do the science necessary to address those assertions, not to dismiss them out of hand. Well, I hope I've showed you that climate change and our understanding of the causes of climate change doesn't rest on one data set alone. We don't just look at surface temperature. We've done this sort of pattern recognition work and looked at climate changes in many different aspects of the climate system, not just temperature. Water vapor, rainfall, circulation patterns, and the bottom line is natural causes alone don't explain what we see. The most parsimonious explanation of the observed changes has to involve a strong human input to the system. People rightly criticize climate models. They're complex numerical constructs. They attempt to simulate a very complex reality. They have strengths, they have weaknesses, but the assertion that we don't compare them with observations, that we have no understanding of their strengths and weaknesses is just plain wrong. People in this room, like Thomas Reichler and many others around the world, compare models with observations in a variety of different innovative ways. So the assertion you guys never compare with reality is just plain wrong. But the science isn't done and dusted. There are plenty of interesting problems left for many of you students in the room. For me, one of the key problems is shrinking those projection uncertainties. If I'm a policymaker and I have to decide on policy responses to the problem of human-caused climate change, whether I can expect to see 2 degrees warming or 5 degrees warming out to 2100 is a big deal. I want to bound the problem better. I want to shrink those projection uncertainties. And again, just maybe there are these clever transfer functions that can relate present-day observables to that projection uncertainty, if we're smart enough, if you're smart enough. Just finally, trust and accountability. A lot of discussion about that in the last couple of years. Some folks have argued in Congress that climate modeling is some shadowy backroom endeavor done by people in these smoke-filled rooms that are never exposed to sunlight. That's not true. As many of you, again, in the room know, our community has worked, Alan and others here, for years to develop software tools that enable people around the world to look at climate model simulation output, to share that output, to understand what's going on, to visualize it. The database, the climate model simulation output that I've described here today, is currently being used by nearly 5,000 scientists around the world. So this has been huge. This has been transformational. Which other field puts its simulation output out there for public scrutiny pretty much within a couple of months of completion of the simulation? And that's really, I would argue, it gives you more eyeballs looking at the simulation output, more diagnosticians, more analysts, and it gives you better insight into what's actually going on in the real world climate system, and better insight into how to improve the models. So, ClimateGate, again, this purloining of 1,000+ emails from the University of East Anglia does not call into question anything I've showed you here today. Various folks have asserted that those stolen emails would cast doubt on all of this, that the planet is warming, that surface temperature data are reliable, that we have some understanding of the causes of climate change. There have been now nearly a dozen investigations into ClimateGate in the UK at Penn State University, and the bottom line is nothing in those emails casts doubt on any of the scientific information. And again, the key point is that this is not a house of cards built on one surface temperature data set developed at one institute. So, my bottom line is that it does not serve any of us well when our elected representatives choose to refer to the science as a hoax, a scam, a conspiracy. We all lose. Climate change is real. I wish it were otherwise. Our best understanding of the science is that there is a substantial human imprint on the observed climate changes we've actually seen. And to stick our heads in the sand, to deny the existence and reality of those changes means that we, and particularly you in the room, will be ill-prepared to deal with them. Again, I think we can't afford to embrace ignorance. In addition to being a scientist, for many years of my life, I've also been a climber and a mountaineer. I spent a lot of time around the world in high alpine environments. And one of the things that I've seen over my lifetime as a mountaineer is profound changes in these environments. Glaciers that I stood on in the Alps are almost gone. That's tremendously sad to me. The recognition that you and others, my son, will experience these beautiful, fragile places in fundamentally different ways is sad. I believe that in addition to the scientific imperative to understand the problem, there is also some ethical and moral imperative to try and preserve some of these beautiful places for future generations. And this final picture was actually taken by Alan many, many years ago when we climbed Mount Rainier. So thank you very much for your attention. I'd be happy to try and answer any questions that you had. And thanks again for inviting me to speak.
Thanks, Ben, for a great talk. We have time for questions for us.
Hi, that was great. Thanks for giving that talk. In your surface, in your temperature graphs, like the satellite and the surface temperatures, there seems to be this kind of slow and steady, ramp that you showed and analyzed. And yet, in some of your measurements of secondary variables, like ice and humidity and so forth, it doesn't seem quite so linear. It seems like they're fairly flat, and then in the last decade or so, they seem to uptick. Is that my imagination, or is that really the case?
No, for things like sea level, there is some sense of acceleration in sea level rise. And I believe the IPCC in its fourth assessment report commented prominently on that over the last 10, 15 years or so, there is in the satellite-based estimates of global mean sea level rise some sense that the slope has changed, that things are happening more rapidly. If you look at Arctic sea ice decline too, one of the things we see there, and this has also been prominently mentioned, is that the observed changes, the observed decrease in Arctic summer sea ice extent seems to outpace what we see in any of these model simulations.
Yeah, that's sort of what I was wondering. Is this outpacing the model, or is this kind of non-linearity, is this some kind of tipping point that's well understood in the models themselves?
Well, again, I think in many of the things that I've talked about, so this fingerprinting is like regression, where you calculate some scaling coefficient between a model predicted spatio-temporal pattern of change and observations. And in many cases, you have to scale up the model pattern in order to best match the observations. That's true for sea level pressure, that's true for rainfall, that's true for Arctic sea ice extent. So in many of these fingerprint detection studies, the observed changes in terms of their spatiotemporal patterns are actually smaller. Sorry, the model changes are actually smaller than observed, which is of concern. I should mention, though, that one possible explanation for that, of course, model response errors are a possible explanation. Model errors in the forcings are a possible explanation. But another is that many of the feedbacks that we know are operative in the real world were not included in this class of model simulations we talked about today. So thawing of permafrost, release of methane from thawing permafrost, carbon cycle feedbacks, those are in newer so-called Earth system models, but not in this class of models we talked about today.
Ganesh?
Yeah, so I was going to ask about the more recent, the catastrophic events that have come to people's attention. So for instance, the sudden increase of tornadoes recently, and the possibility of the western Antarctic ice sheet detaching and things like that. So what are some of the recent studies and observations in that area?
Well, the tornadoes question is a really interesting one, and we were actually asked to prepare a report on that last year for the White House based on the very tragic events of last year in Tuscaloosa and elsewhere. The reality is that this class of models can't explicitly simulate either tornadoes or hurricanes. They're too small scale. They can't be explicitly resolved. What you can do is you can ask how is human-caused climate change affecting the large-scale environmental conditions that are conducive to the development of hurricanes and tornadoes, for example. And we have a lot of understanding about those large-scale environmental conditions that affect genesis and frequency and intensity. In the case of tornadoes, it's things like wind shear, it's things like something called CAPE, so available potential energy from convection, the moisture in the atmosphere. And you can look at this class of simulations and try and understand how are those large-scale conditions changing? Are they changing in a way that might be conducive to the development of more tornadoes or shifting of tornado alley northward? And I have to say the jury is out on that. Rather surprisingly to me, although people have done studies with some individual models, not a lot of that type of work has been done interrogating these large multi-model archives in order to understand whether there's some signal in these large-scale environmental conditions. With regard to the West Antarctic ice sheet, again, the class of models I talked about here does not have in them integrated three-dimensional ice sheet models. That's now starting to change as well. Some groups at Los Alamos, at Berkeley, are now trying to couple three-dimensional ice sheet models for and Antarctica into climate models. And that's important because, of course, as climate changes, you want to know stuff like the channeling of surface meltwater into the base of these ice sheets, particularly Greenland, melting of ice shelves that are actually resting on or in contact with ocean. So hopefully over the next 5 years or so, we'll be able to address your type of question much better than we can now.
Questions?
Yeah, Steve.
So this is a question about essentially the beyond the scientific sphere. 20 years ago, the atmospheric science community had a big win with regard to the ozone holes and the eventual ban of chlorofluorocarbons. Now, granted, the total investment in Freon is much less orders of magnitude than what's in the ground in terms of carbon-based fuels. But are there lessons from that fight that can be extended to the current dilemma?
Well, great question, and people have often looked at the parallels between the stratospheric ozone debate and the greenhouse gas climate change debate. It's interesting that when you go back to the stratospheric ozone debate, many of the things we hear now, this dichotomy, either preserve millions of American jobs or control chlorofluorocarbons. That was pretty much the way it was presented back then, and it's the same now. We are presented with this false dichotomy, as Steve Schneider would have called it, between preserving millions of jobs and doing something about human-caused climate change. I think one lesson from the ozone debate is that a lot of people made a lot of money back then. This scare story, we're going to lose millions of jobs if we do something about regulation of chlorofluorocarbons, it didn't happen. Companies like Dow and ICI found out clever ways of producing substitutes that were less harmful to stratospheric ozone, and they made a lot of money. And I think that's the same here. People who figure out cheap, efficient, low-carbon energy sources are going to make a lot of money. And what I don't want to see, particularly not here in the United States, is some failure of imagination, failure to imagine a different future, that climate up to 2100 can be very different. And we can either be leaders in trying to address that problem, or we can leave the leadership role to others. I prefer us to be leaders.
One more question.
So, I mean, you showed a lot of graphs with average Earth climate, temperature increase over many, many years. So, are you also concerned with, I know human interventions affect temperatures adversely. Either, they increase, or in some places maybe the temperatures dip. So, are you also concerned with, places that show dip in temperature? Have you observed specific locations where there are dip in temperature, and places where there's more than a degree rise in temperature? Like, have you observed such phenomena?
Yeah, that's a great question, and I think at the guts of your question is this issue of signal-to-noise analysis. So global warming, in my opinion, is a bit of a misnomer. It conveys an expectation. It conveys the expectation that each year is going to be inexorably warmer than the previous year. We've never had that expectation. Climate change is not going to cause natural variability to go away. There will still be El Niños, La Niñas, Pacific Decadal Oscillation, North Atlantic Oscillation, all that kind of stuff. That's causing much of this year-to-year and decade-to-decade variability. And indeed, next year maybe we have a big La Nina, maybe cooler than this year. So again, our expectation isn't this linear monotonic increase in temperature at all, nor is it an increase in temperature at every location on the Earth's surface. These sulfide aerosol particles I mentioned to you, they primarily cool. They reflect incoming solar radiation, and they can reduce the amount of incoming solar radiation that you measure at the Earth's surface by up to 30 to 40 watts per square meter. So in heavily polluted areas where there are a lot of these sulfate aerosol particles, they can cool, and that is a human influence, not a natural influence. So I think the key thing is that in trying to disentangle human and natural effects on climate, you need to look at long sweeps of time. You beat down the noise and you enhance the signal, the response to slowly evolving human-caused changes in greenhouse gases by looking at longer periods of time. You wouldn't want to make inferences about the long-term structural behavior of the Dow Jones Index by looking at the minute-to-minute record of day trading of the Dow. It's in the same way, you can't look at one noisy 5 or 10 year period to make reliable influences about causation.